Welcome back to our channel, where we dive deep into the universe's most intriguing puzzles. Today, we're exploring a hot topic in the world of astrophysics, the Hubble tension. This phenomenon might not only reshape our understanding of the cosmos, but also signal a major crisis in cosmology. So, buckle up as we unpack what this means and why it matters. Let's talk about a fascinating discovery from 1929. The universe is expanding. Ever since, scientists like us have been unraveling the secrets of cosmic expansion. Why? Because understanding how fast the universe expands can tell us so much. It clues us into the universe's age, predicts its future, and, perhaps most crucially, lets us sharpen our mathematical models to better describe the cosmos on its grandest scale. For a long time, everything seemed to align perfectly. Our observations across the board supported a consistent expansion rate, matching beautifully with what our theories predicted. It was a golden era for cosmologists. Our models were holding up under scrutiny, and all seemed right in the universe. But then, something intriguing happened. As our tools became more precise and our data more refined, an unexpected discrepancy started to appear. We noticed a mismatch in the measured expansion rates when we looked at relatively nearby cosmic objects. This mismatch challenges our understanding and hints that there's still so much more to explore about our vast, mysterious universe. Let's embark on this journey together today. Exploring the universe's expansion presents us with two fascinating methods: direct measurements of the current expansion rate by observing nearby cosmic objects, and indirect predictions by extrapolating early universe observations to our current era. Interestingly, these two methods don't always agree, and this discrepancy is known as the Hubble tension. Some scholars believe this tension could be a crucial breakthrough, potentially leading us to a radically new understanding of our universe's origin and history. It's like spotting a slight crack in the otherwise sturdy wall of modern cosmology, one that might just open up into new realms of knowledge. But let me set the stage with a spoiler. Many of us think that while this tension is intriguing, it's more likely to refine rather than revolutionize our current theories. It promises a deeper insight into the cosmos, enhancing our grasp of cosmological principles without necessarily rewriting the textbooks. Today, we have the privilege of hearing from an esteemed expert deeply involved in this exploration. Please join me in welcoming to our stage Professor Wendy Fredman. As the John and Marion Sven University Professor of Astronomy and Astrophysics at the University of Chicago and a Fellow of the Royal Society, she has dedicated immense time and effort to unraveling the universe's expansion rate and resolving this captivating cosmic puzzle. Today, we're diving deep into the mysteries of observational cosmology, specifically focusing on our projects measuring the Hubble constant. Thank you so much for joining us, Wendy. Wendy, you've been chasing down the expansion rate of the universe for quite some time. Can you share with us how long that's been? Well, I'm only 42, but let's just say my curiosity sparked around the age of 2. It sounds like understanding the expansion rate of space has been a cornerstone of your professional journey. Is that right? Absolutely. I started delving into this field around the time the Hubble Space Telescope launched, and although I briefly shifted focus, the recent emergence of the Hubble tension pulled me right back in. That's fascinating. And just to give everyone a heads up about where this conversation is heading, it seems you believe that these mysteries will eventually be unraveled, leading to deeper insights rather than overturning our existing cosmic theories. Yes, that's correct. Currently, I don't see any signs that we'll need to completely discard our standard theories. The road ahead is challenging and demands much more precise data to make sense of the complexities we're facing. Let's explore the remarkable one-in-a-million chance that our current understanding might be flawed. However, as of now, the data doesn't support this possibility. What I'd like to do today is put the Hubble tension into a broader context. Let's take a journey through the history of measuring the universe's expansion rate, from its inception to the present, and then speculate on where we might be heading in the next few years.
Taking a step back, it all starts with Albert Einstein. His groundbreaking paper on the general theory of relativity truly set that stage. Imagine us trying to read through his original paper right now in German, no less. That would be quite the challenge, but it underscores the depth of his contribution.
Einstein's ideas revolutionized our understanding of the cosmos. Often, I find myself explaining these complex theories through simpler analogies like a trampoline or a rubber sheet. Do you have a particular way you like to visualize Einstein's teachings? I personally like to reflect on the idea that matter tells space how to curve, and space tells matter how to move. This interplay, first articulated by Einstein, fundamentally changed our grasp of how the universe operates. Let's delve deeper into these concepts and see how they have influenced our measurements of cosmic expansion over the decades. Einstein revolutionized how we understand the forces at play in the cosmos, addressing the age-old problem Newton pondered: action at a distance, and the need for a prime mover to sustain the planets in their orbits around the Sun. Einstein brilliantly unified these concepts, transforming our perception of the universe itself. To illustrate, imagine this vivid visual. Matter isn't just floating in space, it actively shapes the space around it. This curved space, in turn, dictates the trajectories of planets. It's a beautiful, geometric approach to visualizing the very fabric of the cosmos. This groundbreaking theory emerged in 1915, and just 4 years later, in 1919, it was spectacularly confirmed by observations during a solar eclipse. This confirmation inspired other thinkers like Friedman and Lemaitre to apply these ideas not just to the curvature around celestial bodies like the Sun or Earth, but to the vast expanse of the cosmos. It's thrilling to remember these pioneers. They laid the groundwork for everything we know about cosmology. Interestingly, when it came to the notion of an expanding universe, even Einstein was initially hesitant. He acknowledged the mathematical rigor, but resisted the implications. Imagine the tension if Einstein himself had criticized your physics. Yes, he was famously dismissive at times. When he told Georges Lemaitre, a Jesuit priest and brilliant thinker, that his physics was atrocious, it was during the 1927 Solvay conference. Lemaitre approached Einstein with his calculations that suggested the universe was expanding, only to receive a less than enthusiastic response. Despite such daunting feedback, both Friedman and Lemaitre persisted. They knew they were on to something profound, even though at that time we had no concrete evidence of the universe's expansion. Back then, Einstein had manipulated his equations to make the universe appear static, because the observable universe seemed confined to the Milky Way. But thinkers like Alexander Friedman were not deterred. They delved into Einstein's equations and discovered solutions that suggested the universe could be expanding or contracting, and that a stable universe with a cosmological constant was not likely. Then, 5 years after Friedman, Lemaitre, building on this groundwork, used emerging data to support these theories. Interestingly, it wasn't just Edwin Hubble's observations, but also Vesto Slipher's data that Lemaitre used to argue his case. Both contributed crucial pieces to this cosmic puzzle, setting the stage for our current understanding of an expanding universe. Indeed, Lemaitre had a few of Hubble's data points on galactic distances at his disposal, which represented a monumental leap forward. Although he didn't plot the diagram himself, it was Hubble who, in 1929, revealed the groundbreaking relationship between the distance of galaxies and their velocity, an apparent connection that we can actually visualize. We have a graph here that clearly shows this relationship. It's quite remarkable. But let's not overlook the challenges Hubble faced to arrive at that data, the fundamental issue being, how do you accurately determine the distance to celestial bodies just by observing them through a telescope? This is a puzzle that persists even with today's advanced technology. Can you walk us through that critical piece of history, particularly highlighting some unsung heroes of cosmology? For instance, Henrietta Swan Leavitt is a name that doesn't often get mentioned, but her work is absolutely crucial. Every modern astronomical discovery related to distances in the cosmos stands on the foundation she built. Can you share with us exactly what her contribution was? At the dawn of the 20th century, astronomers had mapped the positions of stars across the sky, but the depth of space, the third dimension, remained elusive. Was a star bright because it was close, or faint because it was far. Apart from a few nearby stars, it was impossible to tell. Henrietta Leavitt was pivotal in changing that. In the vast expanse of what we now recognize as the Large Magellanic Cloud and its companion, the Small Magellanic Cloud, Henrietta Swan Leavitt made a groundbreaking observation. Unlike the majority of stars, which maintain a consistent brightness throughout our lifetimes, appearing rather static and unchanging to us here on Earth, she noticed that some stars were different. These stars exhibited fascinating patterns of brightening and dimming over periods ranging from just a few days to about 100 days. Let's take a closer look at some of this remarkable data. Here, we have a photographic plate capturing these very changes. Henrietta would observe the same patch of sky night after night, using these large glass plates as her canvas. By overlaying these images and closely comparing them, particularly in this upper right section here, you can see dramatic shifts in brightness. Watch as one star fades and then glows brightly again. This was the era when astronomers relied on photographic plates to capture and study the cosmos. Night after night, these plates would gather the faint light of distant stars, allowing Henrietta to meticulously chart their varying luminosity. What she ultimately discovered was a profound correlation, a strong link between the period of these brightness changes and the intrinsic luminosity of the stars. Let's dive into a fascinating visual that sheds light on the remarkable relationship between a star's brightness and the rapidity of its luminosity changes. You see, we're talking about Cepheid variables. These are not your average stars. They are supergiants, about 10,000 times as bright as our sun, with outer atmospheres that pulsate in and out dramatically. As these stars expand, their brightness increases, and as they contract, they begin to dim again. What we measure as the mean brightness correlates directly with the period of these pulsations, the time it takes for a star to complete one full cycle of brightening and dimming. Interestingly, the brighter the star, the longer it takes to complete this cycle. This is because larger stars have slower oscillations. So why is this correlation so crucial? It provided us with the key to unlocking the third dimension of cosmic mapping. If we can determine the intrinsic brightness of these Cepheid stars nearby, using a geometric technique, we gain a powerful tool. With this knowledge, we can then look to other star systems, measure the apparent brightness of similar Cepheids, and calculate their distances based on how faint they appear compared to what we know they should be. Imagine the vastness of space and a simple yet profound discovery that helped us map it. Henrietta Leavitt's correlation between the brightness of a star and its pulsation period was groundbreaking, because the luminosity of a star decreases with the square of the distance from us. Her findings allowed us to apply the inverse square law and measure cosmic distances like never before. This method transformed our approach to understanding the cosmos. No longer did astronomers have to ponder whether a star appeared bright because it was nearby, or if it was an incredibly luminous star far away. Now, by measuring how long it takes for a star to complete its brightness cycle, we can determine its distance from us. This is particularly true for Cepheids, whose light curves, characterized by a sharp increase in brightness followed by a gradual decline, are distinctive. Once you identify a Cepheid, you can use what we now call Leavitt's law to measure its distance. And just a fascinating side note, Henrietta Leavitt was finally recognized for her contributions with an obituary in the New York Times this March, nearly 100 years after her passing. It's part of an effort to acknowledge the many women who made significant contributions historically but were overlooked at the time. Did you know about that? It's quite remarkable how her legacy continues to enlighten us even today. It's truly fantastic to see such historic contributions finally recognized. This really enhances our toolkit for mapping the cosmos. But to fully understand Hubble's groundbreaking graph, we need to delve into how he figured out the speed at which galaxies are moving. Hubble discovered something remarkable about the Cepheid variables in these ancient nebulae, known for hundreds of years, by plotting the velocity of a galaxy as a function of its distance from us. He found a clear correlation. Galaxies farther away are speeding away faster. This discovery of velocity was pivotal. Hubble utilized observations made by astronomer Vesto Slipher, though he didn't credit Slipher in his initial publication. These velocities, taken without acknowledgement from Slipher's work, were crucial for Hubble's analysis. Let's circle back to how exactly these speeds are measured. It all comes down to the concept of redshift. As a galaxy moves away, the light it emits stretches towards the red end of the spectrum. By examining how much the spectral lines shift to the red, astronomers can determine the galaxy's speed of recession. This stretching of light, when integrated with Einstein's theories of general relativity, suggested something profound. The entire universe is expanding. So, from these redshifts, or velocities, we glean not just the motion, but the dynamic evolution of the entire cosmos. It's a narrative that beautifully connects Einstein's theoretical framework with empirical data from the depths of space. Measuring these velocities turned out to be surprisingly straightforward, unlike the complex task of determining distances. Here's how it works. Different elements emit light at specific wavelengths, which we can measure precisely in a lab. These wavelengths always appear at the same positions, so when you take a spectrum of a galaxy and compare the positions of these spectral lines, any shift in wavelength gives us a direct measure of the galaxy's velocity. This part of the process is the straightforward part. Getting accurate velocity measurements is quite manageable. However, the real challenge lies in measuring distances. That's the tough part of this cosmic puzzle. But once Hubble compiled his data, he made a groundbreaking contribution with his paper. We showed the graph from that paper just a moment ago. It was this very graph that first made the scientific community seriously consider the possibility that the universe is expanding. With the data he gathered, Hubble was able to calculate the rate of the universe's expansion. Let's look at that plot again, the one showing velocity versus distance. The slope of that graph, what we now call the Hubble-Lemaitre constant, is crucial. Hubble's initial findings indicated an expansion rate of 500 kilometers per megaparsec, which was a pivotal moment in astronomy. We now understand that the Hubble constant is around 70 kilometers per second per megaparsec, which is significantly lower than Hubble's initial estimate of 500. But let's unpack what that really means. Why do we measure cosmic expansion in such peculiar units like kilometers per second per megaparsec? Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.